Alright, so welcome. Today we are introducing proofs. So basically what we're going to be doing is working through some problems and sort of showing how to justify our steps logically, kind of following similar things that we talked about before. This box kind of gives us an introduction to some basic properties. These are the things that we always use when we are solving algebraic equations. So we can add, subtract, multiply, or divide something to both sides and it still remains the same. Reflexive property, think of it like we're looking in a mirror, so everything is equal to itself. Symmetric property, right? That means two halves are the same, so that tells us that when two things are equal, you can flip-flop them across the equal sign and it doesn't lose its value. The transitive property might be new. If you think about it though, it's fairly logical, right? So two things that are equal to the same thing must be equal to each other. And the more common thing that we use in place of transitive or similar to transitive is the substitution property, which tells us that if two things are equal, then we can swap them in and out, right? So we use this when we solve an equation and then plug our number back in to find the measure of an angle or something similar to that. And then finally, we know that distributive property tells us that if we have a number in front of the parentheses, we can multiply to whatever is inside of the parentheses, and it keeps the same value. So in this first example, it's asking us to solve an equation and then justify it. In other words, prove that this equation has an answer of x equals 18, or negative 18. Well, if we're not sure exactly what to do, the first thing we might want to start with is actually solving the equation so that we can see what the steps are. So again, we're going to work it out. So distribute first. And we're going to add the 20. And then finally divide out the negative 5. And if we do that, we should get the answer that they gave us at the start, which we did, so we did everything right. So to turn this into a formal proof, what we're going to do is take what we worked out and break it down into steps. And then we're going to use the properties we were just discussing to justify each of the steps. So if we look at it, we started with the equation that was given to us. So that is given, right? That's always going to be our first step. Always write given. Always start with information that was given to us. So then what do? We distributed. And then we added 20 on both sides. And that is the addition property of equality. Notice I'm writing POE as a shortcut. And finally, we divided everything by 5, or negative 5 in this case, so we use the division property. So when we do formal proofs, this is what it's going to look like. You're always going to have your rules or your statements on the left, and you're going to have your properties on the right. Those are your reasons. So for the next 3 examples, just kind of look at the chart on the front page and try to match up the property being used to make each of those sentences true. And then for C, write out an algebraic proof similar to what we just did. All right, so real quick, the ruler postulate just says that we can measure the length of a line segment using some sort of scale. So it can be a ruler or a number line or an XY grid. It can be anything we want. And then segment addition, we have seen we just add two smaller segments to make a larger segment. So let's see what this looks like in a formal proof, or how we would use it. So what we're going to do is basically look at what was given. So we are told to prove that if CE is congruent to FE and ED is congruent to EG, then CD is congruent to FG. All right, so a lot of words there, right? So let's start with what we know. So CE is congruent to FE, and ED is congruent to EG. Again, we're just marking the parts that are equal. And we need to prove that CD is congruent to FG, so I'm just sort of highlighting so I see what I'm looking at. We are going to want to write our table just like we did. Right? We know we're going to put our statements on the left and our reasons on the right. So what I'm going to do, for the sake of time, is I'm just going to say this stuff right here is given. So when you do this formally, you'll probably need to recopy all that stuff, but for the sake of time, I'm just going to do that. All right, so we know what we have marked. Let's think about what that means. All right, so if two segments are congruent, that means they're equal. So CE has to equal EF, and ED equals EG. And our reason, this is the definition of congruent segments. Okay, we also know that we need to put the two smaller segments together to make the larger segments. So we can say that CE and ED add up to CD, and we can say that FE and EG add to FG. This is our segment addition postulate. All right, here's where the tricky part comes in. So we need to figure out a way to get these two to be equal. So we know that from what we were talking about before, if I have an equation, I can add the same thing to both sides and it still has the same value. So I can take, say, this equation here and add ED to both sides. And that is our addition property of equality. I also know that if two things are equal, then they're interchangeable, right? So that means this CE plus ED is equal to CD. And notice I want FG. I don't have that yet, but ED is equal to EG. So I can take EF and change this second guy to EG. And that's substitution. finally, we said that due to our segment addition, right, we can add the two small segments together and get the large one. Also, we've already written out that FE plus EG equals FG. So we can do another substitution. Which leads us to our final answer. CD is congruent to FG because they are congruent segments. All right, that is a formal geometric proof. I know it seems like it takes a while, but once we kind of get practice with it, hopefully it'll become a little bit easier to do. The example for you to do is basically just filling in the missing pieces, the missing blanks, so it should not take as long. So for our final example, try to run through this pretty quickly. We're going to use our midpoint, right? This is going to be kind of the same idea. So we're given that x is the midpoint of sy. So here's x, here's sy. We're given that z is the midpoint over here. And we're trying to prove that xy is equal, or sorry, we're trying to prove that zf is equal to zf, or sx. So we're going to make our table. Again, I'll do, for the sake of time, I'm just going to copy all the given information down over there. We remember that midpoint means it's exactly in the middle. So that tells me that Sx has to be congruent to xy, and that yz has to be congruent to zf. And that is the definition of midpoint. Well, we know that xy is equal to yz because that's given. And if we're trying to get that zf is equal to sx, all we need to do is make a little bit of substitution. So we know that xy is congruent to zf. Again, we're just substituting. Now we know that Sx is congruent to Zf based on transitive property. Again, transitive property was where when you have two things equal to the same thing, they're equal to each other. And since both were equal to xy, they have to be equal to each other. That's all we have for today. I will see you next time.